Section 9.8 is on finding quadratic models. Let's consider example 1. We've got a set of data that describes the average annual expenditure in thousands of dollars for people in the U.S. at T years of age. The data has been graphed in a scattergram for us here, and in part A we want to look at the scattergram and decide if it's better to use a linear or quadratic function to model. Remember that a linear model is going to have a constant slope, and it's not going to model this data very well at all. However, a quadratic model that's going to come up and go back down is going to be a good fit. So it's going to be a quadratic model since this model is increasing and then decreasing. Anytime your data changes direction, it's going to be a good idea to have quadratic, whether it changes from decreasing to increasing or like this one from increasing to decreasing. In part B, I want to choose 3 points and I want to write the quadratic model by hand. I can choose any 3 points, but I want to look at 3 points that fall nicely on a quadratic model, and I'm going to use data points. This might not be the best choices, but I'm going to pick these 3 data points to go ahead and write my quadratic model. So the points that I've chosen correspond with 30, 46.5, 50, 58.7, and 80, 31.7. I need to plug each of these into the equation for t and for f of t, and then I want to solve for the a, b, c values. So those equations are going to be as follows, and I want to simplify them by just squaring the 30, the 50, and the 80 to have my simplified equation. So my equations will be 46.5 equals 900a plus 30b plus c, 58.7 equals 2500a plus 50b plus c, and 31.7 equals 6400a plus 80b plus c. Now we're going to need to eliminate one of the variables, and c is going to be the easiest variable to eliminate since the coefficients are all 1. So I'm going to take -1 times the top equation and add it to both the other equations to eliminate c in each. -46.5 plus 58.7 gives us 12.2 equals -900 plus 2500 is 1600a, and -30 plus 50 is 20b, and the c's eliminate. Do the same thing with the top equation and the bottom equation. -46.5 plus 31.7 gives -14.8 equals -900 plus 6400 gives 5500a, and -30 plus 80 gives 50b, and the c's add to 0. Now I have 2 more equations. These equations just have a and b, so we're going to eliminate. Let's definitely choose b since b has the smaller coefficient. 20 and 50 both go into 100. So if I multiply the left equation by 5 and the right equation by 2, we're going to be able to get them to both be 100. Now we want them to be negative and positive 100, so let's go 5 and -2 to make the first one 100 and the second one a -100. 5 times 12.2 is 61. 5 times 1600 is going to give us 8000 a plus our 100 b. -2 times -14.8 is going to give us 29.6. -2 times 5500 is going to give us -11,000 a minus 100b. When you add these 2 equations together, the b's are going to eliminate. We're going to get 90.6 equals -3000a. If we divide both sides by -3000, we're going to find our a value. And our a value is about -0.0302. Now you can take your a value and plug it into either of the equations that has a and b to solve for b. I'm going to go ahead and use the first equation here. So 12.2 equals 1600 times -0.0302 plus 20b. If you solve this equation, we're going to get that b is equal to 3.026. Now that we have both the A and B values, we need to plug them into one of the original equations to find C. I'm going to go with the top one because the coefficients are all smallest. Okay, so 46.5 equals 900 times the A value plus 30 times the B value plus C. Let's simplify and solve. Our C value is negative 17.1. If we put these back together to write the equation is going to be f of t equals negative 0.0302 t squared plus 3.026 t minus 17.1. In part D, we want to find the quadratic regression model with our calculator, and then we're going to compare the two models. Let's go back and look at that data. To find the quadratic regression model, you're going to go to your calculator, go to Stat, Edit, and enter all of the data for the age and the expenditures. After the data has been entered in List 1 and List 2, go to Stat again, go over to Calculate. We want a quadratic regression, Quad Reg option 5 for quadratic regression. Make sure that your lists say List 1 and List 2, that's where your data is, and go down to Calculate. If I calculate this regression, the calculator's model is going to be y equals negative 0.0316 x squared, or t squared in our case, plus 3.1606 t plus a negative 20.914. Now that we have our regression model, in part E we want to use a graphing calculator to compare the two models. So we're going to go to our calculator. We're going to enter the first model, the model that we found, in the first y equals line, and the regression model in the second y equals line. Make sure your plot is turned on so that your data is going to graph as well. And we're going to go Zoom Stat to zoom in on the data. So Zoom option 9. So here's the data. The first graph is the model that we chose, and we chose these 3 points, going right through those, but it looks a little bit off. And the red line that's showing up now is the regression model. Okay, the regression model is a little bit under ours, so the model we chose using those 3 points is a little high, but it's actually pretty close to the model that is the best fit, the regression model. Regression recap. Alright, so linear and quadratic are the two types of regression we've looked at so far. Linear are best for data sets that are constantly increasing or constantly decreasing. Some other notes about linear models is that they are eventually going to cross the x-axis and make negative predictions in one direction. So depending on your data set, there may be an area where the model does not make sense, where the model breaks down. Quadratic models. Quadratic models are for data that change direction. So data that either is decreasing and then increasing, or vice versa, increasing and then decreasing. One of the problems about quadratic models is that because they are increasing very rapidly at the end, they're very large for future values of the data. So we have two ways to check to see which model fits best. We can look at the scattergram and observe whether the data looks linear or quadratic, and we can look at the r-squared. The regression that has the r-squared value closest to 1 is guaranteed to be the better model. We can also think about it in terms of the context of the situation. What makes sense? Does it make sense for the model's data to continue in one direction, or does it make sense for the model's data to have a change in direction? Let's talk more about that r-squared value. The r-squared value is the coefficient of determination. The closer to 1, the better the model is. Okay, what is the r-squared for the previous example? When you calculate your regression, you go to Stat Calculate. The r-squared value may or may not appear. It depends on if you have it turned on. So right now my r-squared value is not turned on. I need to turn it on in my catalog. I'm going to go to Second Catalog, Second 0. And I'm going to hit D for diagnostic. So D is right here in green. So I'm going to hit this key. And I need to go down until I see the diag on off, the diagnostic on off option. There they are. Diagnostic off will get rid of the r-squared. Diagnostic on will turn it on. So I'm going to turn my diagnostic on. And just as done, when I go back to Stat, Calculate, and do my quadratic regression again, I don't do anything different. But since my diagnostic has been turned on, it's going to show up along with the values of a, b, and c. So now I see a, b, c, and r squared. The quadratic regression for this data set is 0.97. It's very good. It's very close to 1. So if your r squared value is showing up, you can say that if it's a value that's very close to 1, like 0.97, your quadratic model is a good fit. If I were to do a different model on that same data, that quadratic data, for example, if I was to do a linear model, option 4, I'm going to find that this is not a good fit. Hopefully, let's look at our r squared value for the linear model. Oh yes, that r squared value is very, very small. It's very close to 0. This is in scientific notation, so it's 0.0000202. So a very tiny, tiny r squared value that's not close to 1 at all, so the linear would be a horrible fit. Okay, let's look at the next example. In example 3, we have 2 different scattergrams for this data, and the r squared values are given. So if we look at the burglary data, I can see it does tend downward, but it does so at a slower rate as the data moves on. So the linear model is actually going to have a lower r squared value. The r squared value for linear is 0.77, and the r squared model for quadratic is 0.96. The quadratic model fits the data better. Okay, label each graph. So this one's linear. This is the graph of quadratic. Which model fits better? Quadratic, r squared value closer to 1. And part D asks which model will make the best predictions beyond t equals 22. Let's go back and look at that data. Beyond t equals 22, the linear is going to continue to have a downward trend, but the quadratic, since we've passed the vertex, is going to go up. And it's not as realistic that this data is going to all of a sudden start to spike and go up. So beyond 22, the linear model is going to have the best predictions. So even though quadratic fits the data itself well, the linear is going to make better predictions in the future from this data. It's going to have a better outcome. The quadratic model would be increasing again, like we said, that's not evident by the data. Last page. In example 4, we want to discuss a couple different data sets here. And we want to look at the scattergram, analyze what the best model is for the current data and the best for future predictions, then write the model and the r squared value. So I've already gone ahead and entered these models into my calculator and gotten the regression values, so you can check yours to make sure that yours come out the same. Now this one right here is a linear model. Linear is best for the data and for future predictions since there is no turnaround. It's all increasing. So we've got a linear in both cases, and my linear model is given. It's got an r squared value of 0.99. It's very close to 1, so linear is a good fit for this data. Let's look down at the next 2 examples. These are going to be quadratic models. The first one, quadratic, fits quite well for the data. Quadratic model is also going to be very nice for future predictions, but if you were going to go in the past, you're going to want probably a linear model to talk about data to the left of this data set, because the quadratic model is going to turn around and go all the way up. It's going to say that these data went very large in the past, whereas it was most likely something that was still decreasing. So depending on where you're looking, if you're making predictions in the past, actually linear is going to be a little bit better than the quadratic here. Okay, so our quadratic model that fits our data is given right here in an r squared value of 0.997. The r squared value only tells you about the current data. It can't tell you anything about future or past predictions. And let's look at the last one right here. We've got some more data shown. You can see that it increases and then decreases, so a quadratic model is going to be the best fit for both now and in the future. And model is given, and the r squared value on this one is 0.83. It's not as high as we've been seeing for r squared values, but as you can see, this data set is a little sloppier for a model. It's not quite fitting a perfect curve like the previous 2 sets were. So the model is going to be the best out of the options we're given. It's going to be the best type of model I could have, but it's not going to be as good as if the data was a little bit more evenly distributed. And the last page just has some warnings. The quadratic model will almost always have a higher r squared value than a linear, but that doesn't mean it's better, because quadratic models are more complicated, they're more difficult to solve. So if the data looks linear, you're going to want a linear model. In these 2 data sets right here, linear model is going to be the best set in this one. And in the second set, it's often the case that real-world data isn't as perfectly clean as the first example, but this second set right here is also going to be linear. It's just that you're going to expect your model to kind of hit the average or hit the center. Okay? So if there's no increase, decrease, if there's no change, you're going to call it linear. And the last note about these regressions is that these are just a couple of issues. There are also many other types of models that are not covered in this course. Your calculator has a lot of other options, as you've probably noticed in the Stat Calculate menu. So you'll be getting onto those in the next couple of courses you take. And sometimes some of those other models will be better for a particular data set.